Welcome to the webinar series of the Center for the Subsurface Energy and the Environment. Professor Matt Baloff is the director of the center. My name is Kishore Mahanti. I work in this research center along with all these other professors that you see in this slide. We have a lot of exciting projects, including a bunch of JIPs, which we call here the Industrial Affiliates projects. This goes all the way from hydraulic fracturing to a lot of EOR to reservoir characterization. But today's topic is reservoir simulation, and it comes from the Reservoir Simulation JIP. We are trying to do this once a month, and next month we have another webinar coming up that will be given by Dr. Masha Prodanovic on creating a digital environment that combines data, simulation, and machine learning. So please tune in April 9th at about the same time. With that, let me introduce today's speaker. That's Professor Kami Sapanuri. Kami received his PhD from UT and has been teaching here for the last 35 years. He has published more than 600 papers and graduated 230 master's and PhD students. He's the director of the Reservoir Simulation JIP, and he will talk to us today about the multi-purpose reservoir simulators. So, Kami?
Good afternoon, ladies and gentlemen. I'm thankful for everybody attending this seminar today. I'm going to discuss some of the work that we've been doing for 2-3 decades and where we're going next and how all of these they're going to actually come to a general simulator. And so the title of my talk is Multi-Purpose Reservoir Simulator. And I'll give you some background information and then we move on to further developments. Before going anywhere, I would like to thank all the students, researchers, faculty members, and the Reservoir Simulation JIP's members that they have participated in this program. This is a picture from last year that some of the students, a few JIP members, and some of the collaborators that they're shown in here. I'm thankful for their participation. Without their involvement, none of this would have been possible. To start with, background on reservoir simulators. Reservoir simulators are tools to use to protect hydrocarbon recovery from conventional and unconventional reservoirs, and further now from the renewable energy from some of these reservoirs, such as hydration storage, such as geothermal energy, and so on and so forth. So these simulators that generally they solve equation arising from modeling of fluid flow from oil and gas reservoirs. The governing partial differential equations are discretized using some discretization techniques such as finite differences, finite volume, finite element methods. And basically by doing that, because we are using grid-based discretization, then the griddings become important, as well as the accuracy of the method that are used for discretization becomes very important in using these simulators. So a very quick background on development of simulators, which it goes back now over 60 years or 70 years or so. Some of the work that was done between 50s to 70s, there were basic work that in this area was development of some of the transport equations through porous media. 70s to 80s, there were various reservoir simulators that was very active years that companies and mainly in some universities specifically University of Texas at Austin, with Professor Coates in that era, development of black oil and subsequently compositional, thermal, and dual porosity and chemical, and some of those started during that time. Then in 80s to 90s, if I'm not mistaken, commercial simulators started looking at full implicit method, adaptive implicit method, fast solvers, equation of states, vector computers started in that era. 90 to 2000, geomodeling, geomechanics modeling, using workstation computers, some of them that they were RISC workstation that they were developed in Austin, Texas by IBM. And then, some of the work that they were done in GUIs and all of that, and parallel computers using different technology, they came to the market. And more recently, from in 2000s to present, basically some of the work that has been involved has been in commercial simulators and university simulators that they've been using and are using, and structured grids, large scale simulations with the advances in the computer technologies. People now they're talking about millions and billions of grid blocks using in simulations, and new hardwares, especially GPUs and some of the other technologies that has come to the market that has helped a lot in development of such simulators. Some of the simulators, and I'm sorry, specifically, I'm not covering all the simulators that they exist in the whole world, but some of the simulators, to start with the black oil simulators, that they are used for natural depletion, water flooding. Examples of those are commercial simulators, IMAX, ECL 100, UTComp, that it was developed at the University of Texas at Austin, Nexus, Intersect, and more recently T-Navigator, that they have gone their fast simulation by using GPUs, then going to a compositional equation of state that they are used for miscible and immiscible gas flooding. Simulators that they're used are GEM, ECL, UTComp, Intersect, and T-Navigator. Once again, and I'm sure there are others, but I'm not including everything in here. Compositional K-value thermal, steam drive, SAGD, gas, electrical heating, foam flooding, and these are simulators such as STAR, ECL 300, UT-Therm, once again from University of Texas at Austin, Intersect, and T-Navigator. Chemical flooding, that has been, University of Texas has been one of the leaders in development of this technology, and basically for alkaline flooding, surfactant flooding, polymer ASP, low tension gas flooding, and foam flooding. And UT-Chem is the most well-known and basically leader in this area. More recently, Intersect has some of the capabilities, as well as some of the other simulators, and also T-Navigator has some of the technologies there, but not so much in the surfactant flooding, but polymer, but they have some capabilities in surfactant as well. So before I go to more specific development that we are doing, I'd like to talk about some of the high resolution methods for compositional reservoir simulators that specifically they are used in the simulators that they've been developed at the University of Texas at Austin. And this is an important area, specifically when we're talking about enhanced oil recovery, that we are looking for high resolution results from these simulators. I'm going to give you a couple of very simple examples, but very important equations. One of them is the convection diffusion equation, and some people they refer to this as confusion equation because of the problems that comes about in solving this computationally. And another one is the Buckley-Leverett equation that is quite a bit used in the petroleum industry. And I'm going to discuss with you some of the solutions and approaches that are used for solving this simple equation, because more complicated version of the first equation is actually used in many of our simulators that basically includes everything, including the multidimensionality. Okay, one of the basic method that is used for solution of basically discretization of the first order partial derivative, partial of c respect to x, is the 1-point upstream weighting, or a backward difference, that is shown as c sub I minus c sub I minus 1. It's a first order approximation. And this is one of the basic methods that is used, has been used, in many of the simulators in the market. And basically, when you do this, then I'm using, in this case, a second order approximation for the discretization of the diffusion term, and a first order backward approximation for the first order term. Okay, in this case, the problem is pretty much hyperbolic, because the coefficient in the front of as a Peclet number is a very small number, so it's a Peclet number of 1000. So in this case, the convective term is dominating, and the solution does not oscillate, but it does smear. And this is the number of grid blocks is about 100, and blue is shown as the analytical solution, and the numerical solution is shown as a dashed line, red line. And as you can see, a smearing there. Okay, now if you revert to using central differencing for a convective term, as you can see there, as is shown in here, that basically what I have oscillatory behavior. It's an overshoot. However, the error in this one is not necessarily any smaller or larger than the backward difference on upwinding, but the upwind looks good because it doesn't, deviate basically from in the oscillatory results, and we feel it's better, but both of them, they do have large errors. Now, if you refine the grid, eventually the upwind scheme is going to go or very close to the exact solution, but the central differencing continues to have some very small oscillations. A higher order method that was developed years ago, and quite a bit of work which was done at the University of Texas at Austin, addresses basically a third order approximation. And as you can see there, we have a central point, a forward point, and two backward points in here. And this we just refer to as higher order method. And as you can see there, for the same problem with a Peclet number of 1,100 grid blocks, the solutions are nice in terms of you do not see oscillative behavior and you do not see much of smearing. Okay, and but for the same problem, if you go to the limit of Peclet number of 10,000, even the higher order method oscillates. And as you can see there, the amount of oscillations are very large. So some of the development, and I'm not going through a lot of detail, but I'm giving you some overview on this, that we looked at high resolution method, or TVD, which stands for total variation diminishing method, with flux limiters. And the goodness of this method is that we are using higher order accuracy for smooth regions, and then we are able to resolve the sharp resolution of discontinuities at the front. Okay, and then basically we get rid of the oscillations in the solution. And as you saw that the upwind method, they did not oscillate, they smear, but the central method, they did oscillate. So these were some of the work that was done by us at the University of Texas at Austin, and many other people, mathematicians, they work on that. Specifically, I'm referring to one work that was done by Swaby And I'm giving you the reference at the bottom. And using such method, as you can see there, even with a very large Peckley number of 10,000 and using only 100 grid blocks, you can see there that it resolves the front very well. It almost matches it perfectly. Okay. And here, what I'm doing in here, but of course, in one on the graph in here that is shown in this case, I'm using these flux limiters, and as you can see there, basically the front is nicely resolved. However, if you don't use flux limiting in here, and I'm using here 100 grid blocks, in this case I'm using 800 grid blocks, and as you can see there, even in that case, using the higher order method, we basically have oscillatory results. And then computational costs, because I'm using so many grid blocks, becomes very prohibitive. Okay, very quickly, another equation is the Buckley-Leverett equation in here, and I have applied the same thing in here. Once again, this is the exact solution that is shown in blue, and then we are using the higher order method, but we're not using the TVD limiters, and as you can see there, that basically it does not resolve the sharp front, and as you can see there with the limited is much closer. This is a tough problem to handle because basically, as you can see there, this is a very, very sharp front. Now, this is a 2D problem once again, and there was an exact solution. There's an exact solution that was derived by Dr. Abbaszadeh at Stanford, and as you can see there, this is basically is giving you the analytical solution. Here is the backward difference or 1 point upstream weighting. As you can see there, it did by far, it did not, catch the peak in here, versus the higher order method almost matches the exact solution. So having said that, the results that I have shown you there for a 1D problem, if you're going to use the higher order methods for a 3D problem, the stencil for such a discretization gets more complicated. And as you can see in here, basically I have 27 points that I'm using. And so what you're gaining because of the accuracy, although there is more expense involved in here, at the end, you should come ahead because you gain accuracy and better resolution of the fronts. Some of the development in the gridding area for using basically in our reservoir simulators in petroleum industry, we are using so-called a corner point geometry, a non-orthogonal grid, and more lately we're talking about unstructured grids, and I would like to comment on that. So as you can see there, a given reservoir in here, the boundaries of the reservoir are very irregular, and then you have faults that you have to model accordingly. So the Cartesian grid that is used, it cannot really do a nice job because as you can see there, you have a jagged representation of the boundaries as well as the geological fault or any other irregularity that you have to handle. So traditionally in area of petroleum engineering, many of the simulators that they've been developed, they have the structure but non-orthogonal grid. And as you can see there, it gives you ability to represent the boundaries better, much better than the regular Cartesian grid. But still, there are difficulties when we go to a lot of refinements and doing local refinements and all that. You have to use a special procedure. So some of the more recent development has been in using the unstructured grid. And in the area of unstructured grid, you can resolve the boundaries without much problems or any other areas that needs to be modeled from geological perspective. And however, basically these methods are they are very well, they work very well for the representation of geometries, but there is grid generation and some of the expense that comes into the picture that needs to be handled accordingly. So these are the areas that there is a lot of work is being done, and maybe in the future, there's most simulators, they will have this type of capabilities in this area. We've done work with Professor Maleska from Florianopolis, from Brazil, Professor Marcondes, and some of our work is being joined with them in putting such grading into our reservoir simulators. Okay, now having said that, is that in order to be able to handle a complex geometry, then you need to have not just regular elements. As you can see there in here, I've shown various elements such as hexahedron, tetrahedron, prism, and pyramids in order to be used in various areas of the reservoirs. And as you can see in here is that I can match these by using the pyramid elements, that I can match various types of elements together without too much trouble if I can generate them accordingly. Here is a reservoir that we are basically using 3D reservoirs. And as you can see there, in the areas that is shown in blue, I do have a fault that I need to represent that accordingly. And as you can see in here, that there is one other thing is that probably I want to do a local refinement around the wells and some other areas. Now, here I don't need to really do a local refinement because I can use a different gridding approach and then grid differently around the wellbore and around the fault accordingly. So as you can see there, and even if you go to some of the wellbores that needs to be modeled, I can use different elements to basically model it accordingly. On top of that, as you can see there in here, I have enlarged the faulted area here. And as you can see there, I have basically, I can match the two sides of reservoir by using the pyramid as a transition element in among this whole modeling. So this works pretty well. And what it is this, that quite a bit of work is being done in this area. The approach that we use in most part is we are using finite volume, but because we are borrowing some of the shape different elements from finite elements, the referral as a name to this approach is called element-based finite volume method, or EBFM method. And we have done some work, and there are publications that if anybody's interested, they could be found in the literature in this area. So we feel this is something that worth further investigation in regards to make this more flexible and to be used. So in regards to some of the reservoir simulation development, I would like to bring up in many of the reservoir simulations that they've been developed and are under development, we use a fully implicit, adaptively implicit method or impact method, and I would like to say a few words about that. Okay, the partial differential equations that they are represented the fluid flow to porous media, and further, if you're doing any injection of surfactant or CO2 or whatsoever, you know, these equations, they need to be solved by using some approach, as I indicated previously, finite volume, finite element, finite differences. Depending on how equations are solved, if they're all solved together using implicit method, we refer to as fully implicit. If some of these are solved, basically pressure equation is solved implicitly and the conservation equations are solved explicitly, so we refer to this as impact method. There are approaches that we can mix these two together, and as you can see there, for example, in the areas that we are talking about around the wellbore and high velocities, or other types of things that we need to be careful that we might use implicit approaches in some areas. Implicit method, they are computationally more expensive for per time step. However, it gives you the capability of taking much larger time step if it's needed accordingly. So mixing these would be nice because we could use more of an impact method in the areas that we do not need as much pay attention because of instabilities. And then so we use this method as called adaptively implicit method. And they are fast, and then it preserves the accuracy that we need as well. Okay, so for the solution of such a partial differential equation, as is indicated, we do a time discretizations, and then in most cases, the time discretizations are first or second order, and then depending what you have on the space, it varies. So if we are using an explicit method, as you can see there, that the function is evaluated at the nth level. And if you're using an implicit method, the functions are evaluated at the n+1 level. Okay, now here what it is that because in these simulators, we solve systems of partial differential equations, then discretization of such equation leads into, because in most cases the problem is nonlinear, and of course there are no exact solution, because if you have exact solution, then there's no reason to go to numerics, and you can solve them directly. And so the solution of partial differential equation leads in a set of nonlinear equations, and in most cases we use Newton's method for solving these systems. And obviously, when you're using the Newton's method, you need to linearize the equation, and as such, you need a Jacobian matrix that it needs the partial derivatives that needs to be used. Now, one approach is that you can use finite differences, but of course that gets expensive because for every integral you need a couple of evaluations there. So one approach is that take these partial derivatives by hand, and some of these, depending on how complicated it is, you might spend a couple of months or a month or so to take these partial derivatives. Another approach that is being used is using the automatic differentiation tools, or AD tools. And in this case, basically, you give the code to this other code, and it takes those partial derivatives for you and writes a code for you. And we have done development in our research group using this, and we have made comparison between hand derivative derived versus AD tools. And in some cases, of course, the hand derived methods basically are faster because the explicit function is stated. We've seen within like 5% overhead using the AD tool. So this is another thing that is good. And the other thing is that when you're solving these partial differential equations, because you have sets of equations, you basically choose sets of primary variable versus secondary variables. And depending what you choose for your primary variables to solve the equations, it varies, and different formulations, they come into the pictures. And basically sometimes one formulation works better for a given processes. And that gives the goodness of AD tool, because you could have many of these formulations tested accordingly and pick what you want for a given problem. Now, one of the very famous simulator that is been under development, and it is the UT brand, but it's called University of Texas Chemical Flooding Simulator. And a variant of that simulator is UTChem RS that has more field type capabilities in it. The simulators, either UTChem or UTChem RS, they're used for surfactant flooding, polymer flooding. It can handle water flooding, and of course ASP, alkaline polymer surfactant flooding. And specifically, the UTChem RS has the capability of using implicit pressure, explicit concentration using entirely a full implicit method and also using adaptive implicit method as well. Okay, some of the other features that they are implemented in this in the simulator are the high order method with total variation diminishing and limiters, and it can handle also a discrete fracture that I'm going to talk about it in a few minutes. Okay, now this simulator basically has a capability that to use millions of grid blocks, you know, and it runs fairly fast and very reliable. Okay, and the results are as I said, that the really the chemical flooding is being flourish and further developed at the University of Texas at Austin, and really simulators such as UTChem and UTCOM are the one that when other people they do development, they make comparison to the simulator to make sure that the results are correct accordingly. Okay, as you can see in here that I'm showing for the UTChem RS, we are able to use IMPEC on a PC that has about 32 gigabyte of memory. It's a window based. This is the test that was done. Using IMPEC simulator, you can use about 8 to 9 million grid blocks. Going to AIM or fully implicit, you can use 4 million grid blocks. And if you're going to surfactant flooding is 8 versus 2 million and so on. And then basically what it is that computationally for such a run that is shown in here, about 800,000 grid blocks with 6 injectors and 7 producer. Of course, this was a bigger reservoir, but the active number of grid blocks are about 0.8 million. Okay, and then it took about 3 hours for a 2,000-day simulation doing a polymer flooding, and it took about 8 hours doing a surfactant flooding. Okay, so now if you have computers that they have larger memory and they can handle, of course, many more grid blocks accordingly as needed. There is no limitation. The limitation is how big your machine is. I stated this table in here is not so much that I'm going to go over it, but I thought I put this table in here that shows the various capabilities of various simulators that they have chemical capabilities. These are UTChem, UTChem RS, ECL, T-Navigator, and Intersect. So if later on you're interested to look at this table, I believe this talk will be recorded and it will be on the web that you can see it. So you could have this table for comparison purposes in different areas, from the physics to some of the grading issues and so on and so forth. Another reservoir simulator that is been developed, it's called UTComp, and further development of this simulator has led into a simulator which is called UTComp RS. And basically this simulator has the capability to handle condensate gas, light oil, miscible displacement, water flooding, and solvent flooding, as well as foam and some other features. And this simulator has been further developed in a sense is that at this point it has the capability to have the solution techniques as IMPEC. It has implicit pressure, saturations. It has also a full implicit rather than doing solving it in sequence. You can solve all the equation together. And furthermore, it has the capability to solve the equation on adaptively implicit method. Okay, this simulator has features as high resolution methods that I discussed before, and then also it has capability to run fracture reservoirs, and I will describe that approach in a few minutes. Now, one of the big issues that comes into the pictures are the computational aspect of phase behavior. And then I have shown in here that, as you can see there, this was for a IMPEC, implicit pressure, explicit concentrations, the pressure equation is dominating. The flash calculation is dominating. So these are something that basically what we need really very fast solvers, as well as that. I'm not discussing the solvers issues, but I'm just saying that what are needed in order to have a successful compositional reservoir simulator. So basically we need fast, robust algorithm for flash calculation, as well as the solvers that is needed for these systems of equations. And then these are really multi-phase and multi-component that has to be addressed. Okay, from the geochemistry point of view, there are many different applications that they need geochemistry. One of the recent development in the last decade or so, it's been in the area of low salinity, water flooding, and combination of CO2s and other additives. And basically what it is in here, it shows this was a work that was done by Ali Youssef et al. From Aramco, that it shows by the changing the salinity of water, you are getting incremental oil recovery. Okay, so but this leads to you need a geochemistry engine to handle such as this, that basically in our application, we believe that this is due to weathability alteration, but then we need to use the geochemistry engine to do the calculations. Another application that needs geochemistry is doing acidizing. And in this particular case that I'm showing you in here is that the work that we've done basically with combination of using modification of UT-comp and the acidizing model that basically shows that movement of acid. And in particular, we're talking about carbonate acidizing here. Of course, we've looked at sandstones as well, but creating wormholes. Okay, once again, that needs basically the application of geochemistry modules. And so also, as I will talk about, that it is important to look at a combination of these, the geochemistry with handling fractures, geomechanics, and so on and so forth in the entire simulator. Here shows furthermore that how these wormholes are created, and then this was a experiment, and I'm showing you some of the results of experiment, and similar things would happen in the reservoir. So what it is this, that what we did, we looked at using UT-comp as well as UT-chem, and then we coupled a program that is developed by USGS, US Geological Survey, and this is called iFreaky-C. And of course, what we did a coupling between the R simulator and such a geochemistry engine. And it might be simple as just a coupling, but really it took a whole dissertation and further development in making such a coupling and make this usable in a manner that it is something that computationally would be able to do. So such computations are very expensive, because when you have a geochemistry that is involved with your reservoir simulation, the geochemistry is going to dominate basically the computational area. Two areas that I would say that one is geochemistry, other one is geomechanics, that they're very expensive. The good news is that when we're using the geochemistry, we could decouple this in a sense that, as you can see there in here, I can do the computation of one part of the domain on one processor, and then basically when I'm done there, go back and put things back together. So we are doing really, I don't want to call it parallel processing, it's really distributed processing, because if I have large number of processors and then my usage, then I can divide the reservoir and send that computation to those processors. And when the computation is done, bring the answers back to where it needs to be used. So as I say that for a reasonable size reservoir, it becomes almost impossible to do these computations if you have only one processor. Fortunately, these days, even many of the desktops that we have, they have 8 processors that they could be used for such a procedure. There are other improvements that we did to speed things up, and we have some of these that basically, if anyone is interested, there are papers that we have looked at on these that they were generated by various graduate students and researchers at the University of Texas at Austin. One areas that we have concentrated on is natural fractured reservoirs, and more recently are the hydraulically fractured reservoirs and combination of hydraulics and natural fractured reservoirs. Quite a bit of oil in the world, especially in Middle East, exists in natural fractured reservoirs, and more recently, as I indicated a minute ago, the unconventional reservoirs that fracture becomes important and needs to be addressed. Okay, so some of these are complex fractures, as you can see there. In here, I'm showing a hydraulically fractured reservoirs, and as you can see there, these fractures not necessarily are orthogonal to the wellbores, and then we have to have a capability to model such fractures efficiently and in a manner that be close to what is actually happening in the reservoir. So traditionally, there are basically these methods such as dual porosity model, dual permeability model, and a discrete fracture modeling. Okay, in the dual permeability and dual porosity model, as it can be seen, basically there are fractures that they're shown in here, and there's a matrix in here. But again, that some of these are basically modeled, goes back a long time ago, that they're showing this as a sugar cube. This is the matrix, and then the fractures are in between, and then there is a transfer function between matrix and the fracture, and the assumption is that the oil or whatever is being produced are being produced from the fractures. These methods are fairly fast. As a matter of fact, they work fairly well from a computational point of view, but there is a question about the accuracy of this method, that how well they're actually representing, because using these specifically more recently that we're looking at hydraulic fractures, it may not be beneficial to use such method. Okay, so many people, they're looking at the discrete fractures, and then as you can see there, in this case, I'm showing a structure gridding, and then there is a base grid, and then the fractures are shown by a blue marking in here, as you can see here. These methods these approaches are basically accurate. They can give you good results. The problem becomes that this type of discrete fracture modeling, their computationally, they're very expensive. They're much more expensive than the dual porosity or dual permeability model. Okay, this is some of the work that we've done in here. This was work that was done by Professor Marcondes, and basically, as you can see there, I'm using the same base grid, and then I model the fractures as a very basically narrow grid in here, and putting these, I have one set of grid that handles both the matrix and the fractures. The problem we're running into that, once again, this becomes computationally very expensive, and modeling that becomes very difficult. And we are talking about grid blocks that they are or elements that they're very small next to elements that they're much bigger. It causes some problems there, and as you can see there, I have to go to a very fine grid in order to model such a process. Okay, so the work that we've done quite a bit, and also companies such as Chevron has invested a lot of work and time in this, and these are the they're the areas that they cover as embedded discrete fracture model, or EDFM. So we have two sets of grid in here. One is for the fracture and one for the basic model in here. What we do, we superimpose the fracture into the base grid, and then there is a communication between these. So for a lack of better words, I saw these are really macro level dual porosity models, because I have a communication between the matrix and the fractures. But in this case, I have the ability to basically really have very complicated fracture areas. There is no problem that I can handle the fractures at any angle, any length. Some they could be short, some could be long. They could cross each other or cross the wellbore. There is no basically problem with that. And as you can see there, this I've shown in here the fracture segments. Okay. Now the good news is that in regards to the memory, I don't need to create a whole reservoir for the fracture and then the base grid, because what it is that I can set those fractures from a memory point of view in the arrays, but there are a communication between fractures and the matrix by giving the location. As a matter of fact, one of our group members, Dr. Wei Yu, gave a talk this morning at 9 o'clock at the Bureau of Economic Geology on particularly on embedded and some of embedded discrete fracture and some of the approaches that we are used. And basically you can see that talk there. Okay. Now, as you can see there, I have made a comparison between the dual porosity, explicit fracturing, and a structure grid. And as you can see there, that basically most of methods, they have some drawbacks. For example, when you're using a discrete fracture using the unstructured grid, you know, the problems are some of the gridding and computational efficiencies and so on and so forth. Okay, these we have used application of these for various types of reservoirs, for unconventional, some of the technology that is lately used by something called fishbone. We've done modeling in that. We've done also modeling for doing acidizing when you have fractures around the wellbore, and then we put these existing fractures around the wellbore and do the acidizing and see how the acid moves through this. This is a fishbone technology. There's a company called by the name of Fishbone, and we did some modeling for them that basically acid creates holes around the wellbore to enhance the skin around the wellbore specifically. We've done some modeling on that. We have looked at using the same technology for doing the fault modeling. Okay, and then this has been extended to corner point as well as a structure grid. Very quickly before I run out of time, also we've done work in doing flow assurance for the wellbore, and the flow assurance that we've done has been in area of asphaltene as well as scales. Okay, these are some of the discussion on flow assurance. And the simulator that was developed for doing the flow assurance studies that combines basically the modeling for scales, for asphaltene, as well as some other and remediation of these. Okay. Now, as you can see there, that in the foregoing discussion that I have, there are many different simulators that they've been developed. And what we decided to do to go ahead and combine all of these and go to a multi-purpose simulator framework, or MPS. And the framework does the parallel processing, does all the IOs and all of that. And as you can see there, we will have, and we're having the capability to put the inputs such as very similar to Eclipse simulator, and we will have our own, basically input processor. And then the simulators, the efforts are being made to parallelize everything. And as you can see there, the reason I call this multi-purpose, because it has miscible gas flooding, chemical flooding, thermal flooding. All of these, they will basically use the same sort of gridding. So the gridding modules are separate solvers. Then some of these will be communicating with metrics acidizing, flow assurance, geochemistry, and geomechanics, and the wellbore simulator. We're going further. We are putting the Edfm for all the simulators to handle the discrete fractures modeling. Then we have output. Then we have visualization technology that uses, basically could be using ParaView or S3Graph or some others that we are developing ourselves. Furthermore is that we are putting other types of packages in here to do, such as experimental design studies for various studies in the reservoirs. We have history matching modules that basically we complete the entire simulation. So this is the multi-purpose framework that is being developed, and we are working on it right now. To summarize what I have presented is I talk about various reservoir simulator and their usage. I talk about high order method, talked about grading. Very quickly, I touched upon wellbore and flow assurance, and then naturally and hydraulic fracture reservoirs. And I summarize some of the work that we are doing more recently on the MPS simulator. If you're interested to know more about discrete fracture, about low salinity water flooding, the book that was published in 2017 talks about low salinity. We've done a lot of development that is covered in the 2018 book on the shale gas and tide or reservoir, and we put an entire book on embedded discrete fracture. Some of the history matching that we've been doing and development is coming in the forthcoming book in 2021, should come out in 2-3 months, I hope, on assisted history matching. So with that, I would like to thank everyone for attending the meeting. I'd be happy to answer any question in the time that we have left. I just wanted to comment on a couple of items, to see if there are any questions. I'd be happy to answer. Is that some of the development in here that we've done in here, that we are going to do our work such that we don't want to sacrifice the accuracy only to have a faster, simulator, because we need to keep this such that the simulator would be usable, and hopefully we'll have on the MPS, we'll have enough application on it that could be used by various groups in the companies as well as academia, I hope, that would alleviate reservoir simulation for different EOR processes. The area of fracture that we've done we have worked on, we believe it's accurate, and then they're easy to use. We have developed this software that it could be used with Eclipse simulator, it could be used with CMG simulator, as well as our own simulator. So we're not looking at any part of this MPS code that I was discussing with you could be replaced if you want to bring your own software there. So if you want to use our own, fine. If you want to use somebody else's or your own, it could be done. There is a question. It says that what are the main further reservoir simulation challenges? And yes, there are basically, as I indicated, that still we are striving for getting more accurate method. There are computational difficulties involved, as well as, in regards to numerical method that we want to use, and more including physics, because many of the simulators that they are on the market, they don't have all the features that is needed. The next question is, how do you see the future of reservoir simulation? Do you think data science and classical approaches are going to replace the simulator? Well, to be honest, from where I'm sitting, I hope that's not the case, that these simulators will not be replaced by data science. I have a feeling that this is something that it would complement each other, because even with data science, you still need to use the simulators to train them, right? Can you please comment on the accuracy of EDFM is it true that with Edfm you can use regular larger grid, but does this mean you sacrifice accuracy compared to the discrete fracture method? Well, we have really a lot of simulation that we've done studies, and basically is that yes, we can use larger grid, and in the cases that we need to do some of the mesh refinement, depending how far you go, still the Edfm is faster. This morning, Dr. Wei, you indicated that some of the runs that we are doing, we are gaining up to 20 times speed up than using discrete fracture, actually putting the fractures in. Is there a future plan for MPS to be open source? No. MPS will not be open source because I don't know if you are from a university or you are from a company. The problem that we have is that in order for us to do further development, we need to be funded, and we do not have the luxury of do all the research and publish it without any further, funding. Is the asphaltene option fully implicit? Not at this point. We are really working very hard to make the entire simulator to be fully implicit, impact, as well as adaptive. Okay, and of course it's going to take time, but we will do that. It's the next question is, have you benchmarked the result against commercial simulators? Yes, we have. I cannot mention any particular name of simulators, but for example, in terms of UT Comp RS, we have results that are very comparable in terms of a single processor simulator, because we are further developing the simulator for parallel processing purposes, but to do orange and orange in terms of single processor, we are running comparable to commercial simulators depending on the formulation, and sometimes faster. Of course, we have some features in our simulators that some commercial simulators, they do not have that. So that is one thing. So we'll continue our benchmarking. And also, we are doing some benchmark with our simulator, UTCOM RS, in comparison to the other simulators that they have chemical flooding features. Is there any paper on asphaltene from your group? Absolutely, there are several papers on asphaltene. I would like to thank ADNOC National Oil Company, Abu Dhabi, that they did some of the support for this work that we did on in the area of asphaltene as well as scales. Yes, if you search on Google or under my name, you will find some of those papers. Can we replace the flash calculation with proxy models? Possibly. Some work has been done. We've done some work that's been basically heuristic in some of the phase behavior that has worked very well, but this is something that needs further attention. The question is regarding WOGs, and yes, we have ongoing work at this time. We are collaborating with Petrobras, that we are looking at WOGs from a couple of different point of views. One is fluid flow through WOGs, reservoirs that they're woggy, and also an area that when you're doing acidizing, because when you get to the WOGs, then Darcy flow doesn't apply. So you need to go to Darcy-Navier-Stokes equation or some sort of thing, as you're doing in the wellbore, that you cannot use Darcy equation. So the answer is yes, we are looking at WOGs modeling. Okay, said I would appreciate if you could inform me on the availability of UT simulators. Well, UT simulators, regardless of UTChem, UTChem RS, or UTCOM RS, they're distributed to the companies that they support the development of the simulators. Is there anything that your simulator doesn't do? I'm sure there are many things that our simulator they do not do. What is your advice for people with unlimited access to simulators to get into simulation work? Well, of course, if you're in a, let me publish this. Okay, if you're in a university, of course, that many of the commercial outfits they would give you some of these simulators, and it depends what it is that. To be honest, to say this, that our JIPs are not very expensive to join, because when you're joining any of the JIPs, that the really fabulous work is being performed in all of these JIPs at UT, you're not just getting the money that you put in, you are multiplying by 10 or 20 times. So I urge you to look in, join into some of our JIPs. Do you always use fully implicit method because of the fracture grid have extreme high permeability and a small control volume? I think impact method may not work or has the limitation of very small time steps. Well, to be honest, when you're using Edfm, you're looking at conductivity rather than using very, very small grid. So some of those problems alleviated by using Edfm, as well as the other thing is that if you do not need to use, if you could use orthogonal grids, because the fractures, they're embedded into the base grid. So not necessarily you need to use an structure grid or corner point if needed. But we extended those methods for corner point and a structure grid because if your reservoir simulator is already based on such grid. So I think that you might want to look at some of our work in the Edfm. I believe I have answered all the questions. I really would like to thank everyone who attended this meeting. I'm very thankful for your attendance, as well as thank you very much for asking very good questions. Thanks again, and I hope you all have a nice day.